You know that little red light at the grocery store checkout, the barcode scanner? What if I told you that its existence is directly connected to the fundamental rules that build, well, everything? Today, we're going to follow that thread, from a simple piece of tech all the way down to the very architecture of reality.
And really, this whole story kicks off with a question, a big one, the kind of deep, persistent question only someone like Albert Einstein would ask. And his relentless curiosity, almost by accident, would lay the groundwork for a technology that would completely change our world. So let's jump in our time machine and go back to 1917. Now, Einstein wasn't trying to invent some new gadget or anything. Nope. He was just wrestling with a purely theoretical puzzle, trying to figure out how matter and light interact when something gets hot. And his solution was a stroke of genius that wouldn't really be understood for decades. Just look at that gap. Over 40 years passed between his idea and the first working laser. That's how long it took for the rest of the world, for engineering, to finally catch up to his math. He basically discovered a fundamental law of the universe long before anyone knew what to do with it.
So what was this big idea? It's a process called stimulated emission. And here's the magic trick. An incoming photon hits an excited atom, and bam, out pops a second photon. But this new photon is a perfect identical twin of the first one. Same energy, same direction, perfectly in sync. This idea of being in sync or coherent is the absolute key to everything.
And this is so fundamental that it's literally in the name. Laser is just an acronym for light amplification by, you guessed it, stimulated emission of radiation. So everything from Blu-ray players to industrial welders all goes back to that one wild prediction from 1917. Okay, so we've got it. A laser is all about organizing light particles, photons, into a perfectly coordinated team. But as soon as you understand that, your brain can't help but ask a much, much crazier question. Yeah, could we do the same thing with the actual stuff that makes up our world? Could we line up a beam of electrons or atoms and make them all march in perfect lockstep? Could we build a laser, not of light, but of pure matter? And this is where we hit our first major hurdle. We know the recipe works for light because photons belong to a family of particles called bosons. But electrons, they're different. They're part of another family called fermions. And to figure out if our matter laser is even possible, we have to understand the family rulebook that separates these two. And it turns out, this isn't just some minor family squabble. This is the fundamental dividing line in the universe. The entire subatomic world is split into these two teams, and their completely different behaviors are what makes reality, well, reality. So here's how it breaks down. On one side, you've got the fermions. They're the builders. Think of them as the rugged individualists of the universe. They hate sharing space. Your electrons, your protons, all the stuff you're made of, they're fermions. On the other side are the bosons, the messengers. They are the total social butterflies. They love to crowd into the exact same space, which, you'll remember, is why lasers work. And the one little ID card that separates them, it's a property called spin. The rule for fermions is such a big deal, it gets its own name, the Pauli exclusion principle. It is the ultimate no trespassing sign of the quantum world. And honestly, it's the only reason you're not falling through your floor right now. The electrons in your hand simply refuse, on a fundamental level, to occupy the same space as the electrons in a wall. Okay, so spin is the property that sorts all particles into these two completely different teams. But what even is it? Is an electron actually spinning around like a tiny planet? Well, the truth is, way, way weirder than that. First thing we have to do is just throw out that mental image of a particle as a tiny little dot. That's not what they are. You have to imagine that all of space is filled with these invisible energy fields. An electron isn't a thing, it's a little ripple, an excitation in the electron field. A photon is a ripple in the photon field. And all of a particle's properties, including its spin, are just inherited from its parent field. And this is where your brain might start to melt a little bit. A photon comes from a vector field, which gives it a nice, simple spin of 1. But look at the electron. It comes from something called a spinor field, and it has a property that is just bonkers. You have to rotate an electron a full 720 degrees. That's 2 complete turns just to get it back to looking the way it started. That deeply bizarre, non-intuitive property is what gives it a half-integer spin, and that is what makes it a fermion.
Okay, deep breath. So now we have all the pieces on the board, right? We know about stimulated emission, we know the difference between the social bosons and the loner fermions, and we know it all comes down to quantum spin. So let's go back to our big question. Can we make a laser out of matter?
And the answer is delightfully complicated. It's yes, we absolutely can. And also, no, we absolutely can't, at least not in the way we first imagined. It all depends entirely on which particles we decide to use.
Let's start with the yes. How do we get around that stubborn fermion problem? Well, here's a neat trick. While a single electron is a fermion, we can take a whole atom, and if we add up all its parts just right, the whole thing can behave like a boson. And with these bosonic atoms, we can build something truly incredible.
Here's how it works. You take a cloud of these atoms and you cool them down. And I mean you get them unbelievably cold, just a fraction of a degree above absolute zero. And because they're behaving like good little bosons, they don't stay apart. They all just fall into the exact same quantum state, forming a single, giant superatom called a Bose-Einstein condensate. And from there, you can literally peel off a beam of atoms, all moving in perfect lockstep. A true atom laser.
But what about the no? What about our original idea of a laser made purely of electrons? Well, that's a dead end, because electrons are fermions. They stubbornly obey that Pauli exclusion principle. They will never, ever, ever agree to all pile into the same quantum state. It's just against their very nature. But this is where physicists get really clever. They basically said, okay, if we can't force electrons to become a laser beam, what if we use their rebellious nature to create the most powerful light lasers in the world? In a free electron laser, we accelerate electrons to near the speed of light and wiggle them through a series of magnets. This wiggling forces them to release photons. And here's the genius part. The light they release starts to organize the electrons into little bunches, which then forces the whole group to emit their light in perfect, powerful, coherent waves. We use their independence to create perfect coherence. So let's just take a moment to appreciate the incredible journey we've just been on. It's this beautiful, connected chain of curiosity and discovery that has unfolded over more than a century. I mean, think about it. It all started with Einstein just trying to solve a theoretical puzzle. That led to the laser, a technology based on the social nature of bosons. That inspired us to ask about the loner fermions, which forced us to understand the deep rules of quantum fields. And that knowledge, in turn, allowed us to create two completely new kinds of technology, one that makes matter coherent and another that uses matter's stubbornness to create the world's most brilliant light. And what I find so amazing is what this whole journey reveals. It's just a stunning reminder that the most abstract what-if, curiosity-driven research, like figuring out why a hot object glows, can have consequences that are totally impossible to predict, but that fundamentally reshape our world.
It really makes you wonder, doesn't it? As physicists today explore even stranger ideas, things like string theory or quantum gravity, what world-changing technologies are hiding inside their equations, just waiting for the rest of us to figure them out?